Today I'm going to go over a concept that I just invented for you yesterday called evolutionary reinforcement learning, and it is amazing. I love it. We are going to beat Q learning in terms of performance. If you're a fan of Q learning, if you like Q learning, you're going to love evolutionary reinforcement learning because it's gonna beat it up and down. So, evolutionary reinforcement learning combines a few different principles within AI. The first one is hyperdimensional computing. So, I create random hypervectors, which in this instance I create, in the end result, it's 1,000 dimensional hypervectors. And hypervectors are typically between like 1,000 and 10,000 dimensions. You can up the number of hypervector dimensions in this instance, which would actually increase performance even more than we're seeing now. It would increase computational complexity as well within that. And then I invoke genetic algorithms for evolution. So I'm utilizing swarm-based intelligence, and the genetic algorithms are evolving the swarm-based intelligence. And I'll dive into exactly how that works. Then I utilize multitask adaptation. So the agents get essentially like logic, memory, all types of these things built into their systems and how they function. Then I have utilized optimized reinforcement learning. So I smooth reinforcement learning updates, and then I do utilize benchmarking, which I'll show you here in terms of performance. So let's dive into this. So very specifically, when we dive into this is my notebook of all of my experiments here. And then so what you can see is I start iterating with this performance, right? But what I really want to show you is when I start getting into the actual benchmarks, because that's when we can take a look at these models here. So you can see I'm starting to take a look at performance. And then my first iteration was okay, right? I was getting about 64% performance, and then I couldn't get the model to improve itself, was kind of the bottom line that I was facing there. And then this is my first experiment of my method, like the evolutionary reinforcement learning versus the Q learning method. And then this is just base Q learning, right? And then in this instance, the results were very, very promising, as you can see here, where the evolutionary reinforcement learning algorithm essentially clocking Q learning, right? And then Q learning, there's these dips in it. Let me show you another example of Q learning. Here's another example. That's not the best one. I start getting into multitask, and then this is when I start having to adapt the model, right? I realize that there's more that needs to be done with my algorithm, because there are instances where Q learning is at this point like beating the algorithm, and it's beating it pretty significantly when I start doing this form of testing, right? So I dive into that, and I start going into this further. And let me pull up an experiment here in this notebook. Here we go. This is a perfect and good example here. And then so in this instance, what we have is the baseline of Q learning versus the baseline of the evolutionary reinforcement learning algorithm in this instance. And then what you can see is that the Q learning algorithm has spikes, random spikes, right? Like, to me, this isn't actually learning. And the frustrating thing, if you dive into Q learning, like, this is how the model learns, right? You'll see it, like, and you'll test it, and then like maybe early on you'll get these spikes, right, where it's hitting like 90%, and you're like, man, this is like actually learning, like it's gonna do stuff, right? And then like it'll go from that random spike of like 90% accuracy down to like 30% accuracy. You see it plummets like immediately afterwards, right? The next step from that 90% is a 30%. And then you see like these random spikes where it's like it'll randomly hit very high numbers, like 90%, and then the next is like 20% or random guessing, and things like worse than random guessing in some of these instances, right? And then so it's like in these instances, I mean, with Q learning algorithms, it's been my problem with it overall. Like, I don't really see this as learning, right? There, I don't see this as like retaining information. I don't know 100% what happens within Q learning to get it to eventually start converging, right? If you run this for like hours and hours and days, what will happen is that Q learning starts to converge, right? Whereas I want to get that convergence up front, which is why I have evolutionary reinforcement learning in this instance, right? And then so let's dive further in this instance. So I improve it more, right? This is where I get it to where essentially I want it to be on all levels. That first test, but this is across like multi-modalities. So this is the instance of like the full benchmark testing, where in this instance we can see that this method is not going to lose to the Q learning method overall. And I beef up the Q learning method in this test to make it a very fair comparison. I give it like a DQN, so deep Q learning network. and then essentially going through what this model does and like looking at the code here. So very specifically, this is a lot of code, right? But so I can go through like a lot of this model here. This does, for the swarm optimization, I'm very much utilizing my swarm queen optimization method. Within this, it's very important within this particular framework, right? So up front, as you can see, hyperdimensional computing, I have 1,000 hypervectors that I'm computing in this instance. And then I just randomly generate the vectors up front. And then we have our standard Q-learning baseline for our testing purposes. So this is just, the basis for comparison. And then we have our swarm agents. And then so the swarm agents, how they work is that they are infused with genetic algorithms as well. And then they also have a memory built in. And then they have, and they utilize a sparse representation of Q values for their memory efficiency. So I take a part of Q learning and I essentially build it literally into each one of these swarm agents and into the genetic algorithm itself. And then they go through and then they mutate, and then essentially the parents have this. So you have your parents, and then the offspring is that you take a certain percentage of the population, right? So in this instance, they'll go through and then they'll simulate and then they'll learn, and then the best agents, like the parents of them, they pass off a blended part of their offspring, and then they can also mutate within that. And then also what I can do within this is that if the learning rates start to stagnate and like the population gets too stagnant, then the swarm queen can start adding brand new agents within this, right? So that's kind of a another unique aspect within this framework. Is so it has tournament selection, as you can see here, and then I've got diversity metrics that I calculate out, and then I do a bunch of calculations for diversity, and then at any point, if diversity does get low, we just throw in brand new agents, right? Like so, it's like this agent didn't exist, period, in this framework whatsoever before. And then so we just throw them in, and then now they do, right? And then also too, what I have in this, this is very unique within this model, is that there's a knowledge transfer process from the parent to the offspring, and the offspring inherits some of the Q values. So again, the Q memory or memory mechanism for these agents is utilizing the Q algorithm. And then so within that, whatever their Q values are and their stored Q values, they pass those stored Q values, or some of them, onto their offspring. So their offspring aren't starting off from 0 every time. And then that is essentially what allows us to grow this out. As you can see here, this is the definitions for how the population evolves. We preserve elites, so we're going for very much elitism in this instance, right? We want the best offspring, and then only the best offspring is what mutates into the next generation and then passes their traits on to the next generation. And then so we just do that over and over again, with the queen being in charge of making sure and dictating, adding any sort of rules. So you can see here that in this instance, after iteration 20, the queen throws in 12 more agents, right? Because we start to get stagnation here, we see this drop. And then throws in 12 more agents, and then we get more performance, right? And then it's starting to stagnate again. So my assumption would be, if we ran it past, let's say step 50, that the swarm queen would again throw more agents into here, right? That's what we would see if I had let this run longer, because that's what this pattern shows, and that's what the model is designed to do overall. But then when we lay this over to, and we lay it over the Q learning algorithm, I mean, it's very apparent which one of these is superior. I don't think I need to provide any more test evidence than this overall. And then so very simplistically and straightforward, this is all just mathematics, right? I'm taking the standard Q learning algorithm, but I'm just adding different frameworks on top of it, and then essentially optimizing it mathematically and utilizing mathematics and physics in this instance to create a better algorithm. And then so in this instance, this is MIT licensed. This is open to everyone. I'm not I'm not a fan of patent trolling anything like this, right? And then so my big thing is okay, if someone were to, if I were to instead patent this out as opposed to MIT license it, someone very specifically and simplistically could and should just go in here and then change a few elements within this, right? Maybe they don't use swarm queen optimization, maybe they use something else. They would have to use HDC, but you can't patent HDC on its own, right? Like all of these elements are made up of individual elements that can't be patented on their own. The only thing that I could patent in this instance would be this exact framework. And then I'd be selling you like, here's the only framework that works, right? And then I'd be one of those people. And then so you see people that they tie themselves financially to these things, and then like that's the biggest differentiation that you see. Like I don't tie myself financially to a single one of these things so that I can tell you exactly how it is, right? I'm releasing this open source. I'm telling you that it's the best on the market. I don't have financial incentive behind that. Like if I'm telling that based off of just my own benchmarks here, what I'm doing, it's MIT license. You can prove me wrong. Here's the code for you. Go at it, right? I'm not out here saying like, hey, I patented this, pay me money in order to use it, and then find out if it works. I'm saying, hey, here's all the code. Do it yourself. Prove me wrong. If you think I'm an idiot, then sure. Let's talk about code, right? As long as you stick it to the code, then that's fine with me. If you have problems with my code, with this algorithm overall, let me know. If you want to discuss like philosophy related to AI or like that, I'm going to dog you on this channel flat out. That's just the bottom line of how I handle those things. And then so if you like this type of content, please like and subscribe. Thank you very much.